Good evening. Today's class will be on basic principles of work in the analytical laboratory and classical methods of analysis. The portion on the classical methods of analysis, which will include volumetric and gravimetric analysis, will be taken as a separate webinar on May 16th, 11:30 in the morning, because it will be too much to cover today. The carbohydrate webinar will be repeated on May 3rd, Friday, May 3rd in the morning, 11:30 a.m. So now let us look at what are the basic principles that you should be aware of in an analytical laboratory. I'm going to start from the basic, that is the SI units of measurement, to a large number of calculations that you need to know when you are making solutions. It involves simple math, just addition, subtraction, multiplication, and some algebraic rearrangements. But I want you to listen carefully and look at it. And at the end of the webinar, go back home and try and work some problems for these type of questions, because there will be many of these questions in the food analyst exam. So if you look, okay, what are the base units of measurement in the SI system? So if you see, we have these 7 basic units from which all other units are derived. So these basic units are the base unit of mass, which is the kilogram, and the kilogram is a mass, a 1 kilogram mass of platinum iridium, which is actually kept in a museum in Paris, and it is going to be shifted. It's going to be shifted to another place. So mass, the SI unit is kilogram. Then you have length, which is a meter. It is defined as the distance traveled by light in vacuum during an interval of 1 by 299,792,458 of a second. Then you have time. So you see the basic unit is second. The second is the duration of this large number of periods of the radiation corresponding to the transition between 2 hyperfine levels of ground state. It's not necessary to know these definitions, but we need to know what these 7 base units are. Then you have temperature, which the SI unit is Kelvin, capital K. Then you have current, which is an ampere, and we do not use much of this in our analytical measurements. Then you have the amount of the substance, which is mole, which is used very much in analytical chemistry. Then you have luminous intensity, which is the candela, which we don't use in a food analysis or in a food analytical laboratory. So what are the standard prefixes for these measurements? So the kilogram is the measurement of mass, or even in terms of the distance. So a kilogram is given as small k, and the multiplying factor for it is 3, because 1 kilogram gives you 1000 grams. So now we look at these numbers that is important for us, because you will come across the symbols of centi, milli, micro, nano, pico, femto, atto. So you need to know that milli is 10 to the power of minus 3, micro is 10 to the power of minus 6, nano is 10 to the power of minus 9, pico is 10 to the power of minus 12. So these are more important. These smaller numbers are more important rather than the larger numbers. These larger numbers, where do you come across? You come across them in terms of the bytes. You have 1 terabyte RAM or 1 gigabyte RAM. So those are for different purposes. But we need to know, if I ask you to convert a, the number from kilogram to picogram, you should be able to do it. And if I give you the picogram value and ask you for the value in kilograms, you should be able to convert it to kilograms. So that is the reason why this table has been shown and indicated which of them are really very uh, important in calculations. The second point we need to understand is that when we talk of weighing any sample, you always say weight, but actually it is the mass of the sample. So there is a difference between mass and weight, and very often we are using this interchangeably, although they have got different meanings. Mass is an object, is the amount of the material it contains, and it is measured in metric units, and it is measured with a balance. That is, a balance is used to measure the known amount of water, known amount of matter. Weight, I think almost all of you know, is the force arising from the interaction of the mass with the Earth's gravitational field, or it is the gravitational pull, and the weight is measured on a scale. And weight varies from the location, whereas the mass will not vary. Mass will be the same. So if I buy 1 kilogram of atta in Mysore, it will be the same weight as in it will be the same mass in the US, but the weight will be different because the Earth's gravitational pull is different. So please remember that now you know the difference between mass and weight. Please use these terms as mass and weight. So how do we measure mass? Mass is measured by means of using a balance, and it is a fundamental piece of equipment that you will find in all laboratories. Sometimes in each room you might have a balance or two. There are three types of balances which are used. One is the top loading balance that you know is there. This is a rough balance, or it has got an open pan. You load from the top. It is not enclosed. The body is not enclosed. It's very easy to clean, and it is generally used for making buffers, uh, qualitative reagents, and microbiological media, where the accuracy or the sensitivity is not a parameter. Then you have the analytical balance, which is used for precision weighing. So the precision of these analytical balances can vary from the first decimal, from 0.1 to about 0.01 milligram. That means in terms of kilograms, it is 5 decimal places. It is normally used to weigh small quantities of material, and the error with these analytical balances is very low. When you want to do very high precision work, you use the microanalytical balance, where the precision you see is 0.001 milligram. You can read sometimes even to the fourth decimal place or the fifth decimal place. It is normally used to weigh minute quantities less than 0.1 gram, often to make up standard solutions or PPB solution or a PPM solution. I will be explaining to you what these PPB and PPM solutions are, how to make them. So, which balance do you select for which type of weighing? So let us start with the rough balance, or what we call as the top pan balance. So you could use this for rough weighing, and you have to see the weighing capacity of the balance. That means from about 100 grams and above, you can use the top pan balance. You will see the resolution is about 10 milligrams and 100 milligrams. But if you look at the specification, the exact resolution will be given and the readability will be given. Then you have the precision balance, which is in between the analytical and the top pan balance. Then you have a semi-micro balance, which could be between the analytical micro balance and analytical balance. And then you have the ultra micro balance. So the top three come in the micro analytical balances. These two come under the analytical balance, and this comes under the top balance. So you will see the readability of the balance itself will give you the sensitivity of the balance, and you will, from the readability, know for which the balance has to be used. So we will not expect you to, when you are asked to weigh 100 grams, to go and use a precision balance. And when we ask you to weigh 50 milligrams, we do not expect that you will go and weigh in the top pan balance. You will have to weigh in an analytical balance or in a semi-micro balance. So what are the weighing techniques? Generally, there are two techniques for weighing, what we call as direct weighing or indirect weighing. In direct weighing, you weigh the container that you want to transfer the material. You tear the balance or make it zero. Then you add or transfer the sample to it, weigh the amount, and then using the weigh boat or a beaker, if you have used to weigh, you transfer it into the volumetric flask if you're making a standard. The disadvantage over here is when you transfer from the weigh boat or the beaker that you have weighed it, there are chances that material will stick to it. Although the technique used is to actually wash the weigh boat or the beaker with small amounts, small aliquots of water. However, more accurate than the direct weighing is the indirect weighing. So many of you might be doing the indirect weighing already. This is also known as weighing by difference. So you weigh the material using a weigh boat, take the mass of the weigh boat with the weighing material, transfer the material to the flask or the volumetric flask or other flask that you are going to use for the solution, and then reweigh the boat, and the difference in mass between the two will give you the exact amount of material that has been transferred into the standard flask for making the solution. So this is known as weighing by difference, and it is more accurate, and it is the method which is preferred in an analytical laboratory. Then we come to measurement of volume. We have a large amount of volumetric glassware in the laboratory, and this volumetric glassware is designed for measuring different volumes. I don't know how many of you have looked at the volumetric glassware, especially the standard flasks, the volumetric flasks, the measuring cylinder, and the pipettes. And if you have noticed an inscription on them which says TC or TD. What does this stand for? So the pipettes or the standard flasks, if it says TC, all the standard flasks will say TC. It is meant that to contain. And if you have 2D, what you see in pipettes, That means it is to deliver. The TC in glassware are designed to contain a known volume of the solution. So you will see that all the um, standard flasks have got TC, and you will also see that the graduated cylinders, and you will see the bulb pipettes, or what we call as the volumetric pipettes, which have TD to deliver. They deliver that quantity of water. And the difference between the TC and TD is that in the two deliver pipettes, whatever volume markings are there, the wetting of the glassware, water has the adhesion properties, so it can stick to the sides of the glassware. All this has been taken into consideration when the pipettes have been calibrated. So precise volumes must always be measured at a particular temperature, because volume varies with the temperature. Either there can be thermal expansion or thermal contraction. So whenever you do a volumetric measurement, the temperature must be measured and indicated. For example, water at 10 degrees centigrade has a much smaller volume than water which is at 80 degrees centigrade, to show you that the volume varies with temperature. So any measurement you make in terms of volume indicate the temperature at which it was measured. So if you look at the standard flask or the volumetric flask, you have it. So if you look at the flask, it is either a flat bottom flask with a very narrow neck. It generally should not be held by the neck, because if you hold it at the neck and your hands are warm, temperature differences can occur. Generally, it is held by the flat bottom part of it. It is calibrated to precisely contain a precise volume. So if you look at the markings, and if you have not seen these markings and understood what these markings are, if you look at them, what it clearly says is 50 ml. So that means this is a 50 ml volumetric flask. If you see TC, that means to contain. So it will contain 50 ml. At the measured volume of 50 ml is at 20 degrees. So this is the temperature. This number here is the accuracy or the precision of the measurement. So therefore, this volumetric flask will contain 50 plus or minus 0.05 milliliters. And this white portion is for writing the label on it, because you generally are not expected to put a sticker on it. So TC is the TN, indicating that it is to contain a volumetric flask. Okay, this should have been 20 degrees. And then you have this number A or B. And here this is a class A. This is the manufacturing standard. And for all accurate and precise analysis, the A grade or the class A glassware should be used. So in the volumetric pipette, now that you have volumetric pipettes, there are different types of pipettes. There's one is the volumetric pipette, the other is the serological pipette, and the third is the Moore pipette. Three types of pipettes are available. The volumetric pipette is also known as a bulb pipette, which has this characteristic bulge in the center. There are no graduations in the pipette except the mark to tell you the volume of the pipette. They are open-ended. They have a long glass tube at the upper and the lower end, there is a single graduation mark, and these pipettes are all designed and calibrated to deliver. So if it says 5 ml, it will deliver 5 ml. If it says 25, it will deliver 25 ml. These volumetric pipettes, when you take a solution and you measure it into a conical flask or an Erlenmeyer flask in volumetric analysis, you will see that there is some liquid left at the tip of the pipette. Since this is a two deliver pipette, this volume which is at the tip should not be blown out, because the calibration has been done taking into account this wetting and the volume that is thing. So please remember that a volumetric bulb pipette or a volumetric pipette, even if you see a small amount of the liquid, after allowing it to drain along the sides of the conical flask, it should not be blown out. So if it is blown out, you will get error. So remember that in the volumetric two deliver pipettes, that little bit of liquid remaining should always be left over there. This is very important in analytical chemistry. So here in the pipette, if you look at the markings on the pipette, if you look at the pipette, A says that it is a class A pipette. So that means the accuracy is within 0.02, even though it is not written here. But we know that in the class A pipettes, that is the tolerance limit. TD indicates that it is a two deliver pipette. That means you just let down the liquid and simply drain it out. This time given over here is the time taken for the liquid to drain. When you pipette 10 ml, because this is a 10 ml pipette, if you pipette 10 ml and allow it to drain, it should drain within 25 seconds. And all these parameters, that is 10 ml in 25 seconds with an error of 0.02, will occur only at 20 degrees Celsius. So here you have, this is the top of a measuring cylinder. So in the measuring cylinder also you see a measuring cylinder can be used for delivering as well as containing. And this measuring cylinder you see has both TC and TD, and this is at 25 degrees Celsius. So you see, very important, where the temperature plays an important role and the temperature is always mentioned. Then you come to the graduated pipettes that most of you are used to using in the laboratory. In that we have the two pipettes, that is the serological pipette and we have the Moore pipette. In the serological pipette, the markings, that is the calibration markings, go all the way to the tip. So if this is a 10 ml pipette, this will be 9.5 and to this end of the tip will be 10. This also is a two deliver pipette. It is most often used in the laboratory, especially when you are doing titrimetry and you have to deliver small volumes of liquid. You can measure the volumes by difference, or you can allow it to go through. Very often the serological pipettes will have two frosted rings or two colored rings here, or it might be a broad band that you can identify a serological pipette. Again, over here, the frosted serological pipette, in this case, in the case of the serological pipette, when you have the rings over here, it is indicated that you blow it out, unlike the volumetric pipette. So the serological pipette is a blowout, and blowout doesn't mean blowing with your mouth. you have to use either a pipette bulb, okay, so or a pipetter to transfer the full amount of it. The Moore pipette also is a graduated pipette, which has graduations from the top to the bottom, but you will see that the graduations stop at the one end of the pipette, and it is not a blow out pipette. It is not a blowout pipette. You can pipe it out by difference, okay, the fine and record the final volume. But what is essential in the lab is that whether you use a volumetric pipette, a graduated blowout pipette, or a Moore pipette, no pipetting by mouth. You have to use a pipetting aid such as a bulb or a pipetter. Then we have the burette. All the burettes are to deliver burettes, so they are used for delivery. The burette also generally contains or is used for titrimetry, that is a volumetric analysis. You have a scale on the side which allows you to precisely measure. All the burettes that you use in the laboratory must be class A, which gives you the tolerance limit. So you see for a 50 ml pipette, the tolerance limit is plus or minus 0.1. You have to see that your pipette is very clean, and for precise and accurate work, if you find that when you wash a pipette, water sticks to the sides of the tube, that indicates that it is not clean and it has to be cleaned again. So when you want to check for the cleanliness, water should flow through without sticking to the sides of the burette. So these tolerances for the class A and class B pipettes are, you can find these tolerances from the National Institute. NIST has the tolerances. So while using a burette or a pipette or a standard flask, reading of the liquid level is very important. So you have to see, because whenever you measure a liquid, you will see that there is a curvature. And we have seen in our webinar on water that you will see either a concave or you will see a convex surface. So a concave meniscus will be seen when the molecules in the glass tube have a strong attraction to the glass or the container. And you will see a convex meniscus when the liquid in the burette or the pipette, when the attraction to themselves is greater than to the container, as we saw of mercury. In whichever way, whether it is a concave meniscus or it is a convex meniscus, we have to see that there is no parallax error. So what is parallax error? Parallax error is the change in the direction of observing the meniscus. So if you see this measurement here, if you're trying to see the meniscus from the top, so what happens is you are overreading it. So almost by 1 ml. If you look at it from the bottom, you are actually underreading it. So both these cause errors. So the correct way is to keep your eye in parallel to the lower meniscus and take the reading. Very often when the liquid is there, it is very difficult to look at the meniscus clearly. And if you use a black paper behind the burette or the pipette, the meniscus becomes very clear and you can get accurate readings. If you follow all this, you will see that your triplicate readings will almost be identical when you do any titrimetric analysis or volumetric analysis. So the glassware that you use in the lab has to be very accurate, and it should be made of the material that it is, of the glass that is required to be used for that particular glassware. So in the volumetric glassware, you know, in any measurement, there can be errors. So there is a certain standard deviation and error. The maximum allowable error for the volumetric glassware are set by the National Institutes of Standard and Technology, USA. So in the glassware, we have what is the class A glassware and class B glassware. It is expected that for all high accuracy experiments and analytical measurements that you use only class A glassware. The class A glassware are more expensive than the class B glassware, but for precision, you need to use the class A glassware. And each piece of class A glassware that you obtain, the supplier will give you a certificate which has all the tolerance limits, the calibration, and there will be a serial number on the certificate. And this glassware, the class A glassware, will always have A etched on it, like what we saw in the previous slides. Class B glassware are general purpose glassware, and they can be used for making reagents, qualitative reagents, making media, etc. The tolerance limit of the class B's glassware will be 2 times that of the class A glassware. If you remember the pipette that we saw, the tolerance for the class A was given as plus or minus 0.02. A class B pipette of the same volume will have a tolerance of 0.04. Many a time you might see class AS written on it. What it indicates is that it is the class A glassware, but the S stands for swift delivery. That means very fast delivery of the solution. So there will be some modification in the tip so that the liquid is delivered very swiftly. Other than this difference, there is no difference between the class A and the class AS in terms of the tolerance limit. So here are some glassware that you can see. This is a measuring cylinder of class A. You see, this is a measuring cylinder of class B. Here you have a pipette, which is of class A. It's a 15 ml pipette. It is to deliver. It will deliver within 15 seconds. This plus 15 seconds says that this plus 15 says the delivery time for the thing is that you should wait at least 15 seconds after the liquid has flowed down. So at 15 ml, so you have plus or minus 0.03 at 20 degrees Celsius, and this plus 15 says you should wait for at least 15 seconds touching the side of the pipette tip to the inside of the flask or the beaker for delivery. And here you see you have a class AS pipette. So it is similar to this pipette. Everything is the same, but there is swift delivery of the liquid. That means the tip of the pipette tip will be, the mouth will be much wider. Now coming to the temperature scale. The temperature scale is most often in Celsius, but in the Western countries, it is given as Fahrenheit, and it is calibrated in either degrees Celsius or degrees Fahrenheit. The Celsius scale is called the centigrade. The reason why it got its name centigrade is the melting point or freezing point of water is 0, whereas the boiling point of water is 100 degrees. And this 100 can be divided into 100 equal parts. And so therefore centi means 100. And so the Celsius scale came to be also known as the centigrade scale. It is a scale commonly used in scientific work and in everyday use in most countries. But however, you can convert the Celsius to Fahrenheit by using this formula: F minus 32 divided by 9 is equal to C by 5. You might have studied this in school. You must remember this formula if you are asked to convert Celsius into Fahrenheit or Fahrenheit into Celsius. The other scale that is used is the Kelvin scale, and the Kelvin scale is the degrees centigrade plus 273. So 0 degrees Celsius is 273 degrees Kelvin. So if you have 20 degrees Celsius, it will be 293 degrees Kelvin. Many calculations require, especially the thermodynamic calculations, require that the temperature be given in the Kelvin scale. Then we have pressure, used quite often in the laboratory, especially when we are dealing with vacuum. When you're using a vacuum oven or you're using a vacuum pump, you need to know what the pressure is. So the pressure is the force per unit area. It is defined as the force per unit area, and it is given by the formula P is equal to force by A. The standard SI unit is Pascal, which is given by capital P and A, which is equivalent to 1 Newton per square meter, or the kilopascal, where the kilopascal is equal to 1000. But you will see that the pressure is expressed in many different units, especially in the high-end equipment such as the HPLC, which is using pumps, or you're looking at the mass spectrometer, which has to be in vacuum. So the pressure can be expressed in as atmospheres, where it is equal to 760 centimeters of mercury or 760 millimeters of mercury. You can have it in kilopascal. Vacuum is generally expressed because it is very low pressure. It is expressed as millimeters of mercury. So generally expressed as torr. So 1 torr is 1 millimeter of mercury. And in the HPLC columns that are used, you will see that the pressure is expressed as PSI, and that is pounds per square inch. And you should be able to convert using these formulas. You should be able to convert the pascals into PSI, PSI into torr, etc. Then we come to density. The density of a substance is a measure of the compactness of the matter, and it indicates the mass per unit volume. Density is an intrinsic property because it does not depend on how much of the sample you have, but rather what the sample is made up of. So the symbol for density is given by the Greek letter rho. So rho is equal to mass by volume. You can measure density by using the balance and by using a measuring cylinder or any volumetric thing to get the density, where rho is equal to mass by volume. However, you can also measure the density by using the hydrometer, which is a bulb filled with a heavy liquid or with heavy steel balls at the bottom and graduated to show you what the density is. And the best example of a hydrometer is the lactometer, which is calibrated to show you the density of milk. So the lactometer is a hygrometer. And once again, while taking the readings on the hygrometers, the parallax error has to be taken care of. You can also measure density and specific gravity by using a flask called the pycnometer. So the pycnometer is shown here. So the advantage of using a pycnometer is that you can fill the liquid through this side arm, and the pycnometer is of a known volume. The excess volume of what is in the flask will go into the capillary or the stopper, and you know the exact volume, and you can measure the weigh the flask with the stopper, without the stopper, with the liquid, and get the relative density, the density and the specific gravity. Specific gravity is dimensionless, whereas density has a dimension, and we usually express it in grams per milliliter or grams per cubic centimeter or kilograms per liter. Specific gravity is dimensionless because it is a ratio of the density of the substance to the density of water. Since the density of water is 1, specific gravity is the same as the density, except it does not have a unit of expression. Then we come to the pH meter in the laboratory. This is used to measure the pH or the hydrogen ion concentration. And I'm not going to tell you about the hydrogen ion concentration and how to convert hydrogen ion concentration into pH and pH into hydrogen ion concentration, because we have looked at that in detail when the webinar on water was conducted. So the pH meter, if you look at it, has two components. One is the pH meter itself, which is actually a moving coil galvanometer, and it has a scale and which we read. It is the digital scale that we read. The second part of the pH meter is the most important part of it, which actually measures the hydrogen ion concentration, and that is the electrode. So the electrode, there are two types of electrodes. Sometimes a pH meter comes with a single electrode. Sometimes it comes with dual electrodes. So when it comes with two electrodes, the second electrode is the reference electrode, and the first electrode is the measuring electrode. And so the pH is measured relative to the other reference thing. And so therefore pH also, you see, we do not have, we just say pH 1.0. We do not have any unit for this. However, if you have only one probe in your pH meter, you will find that both the reference electrode and the electrode that you're using for measuring the pH are built in together. So just let us have a look at that so that you understand the working of the electrode. So here is the pH electrode. So if you look at a combined electrode, this is called a combined electrode. It must contain have the pH responsive electrode, and it must have the reference electrode. So the reference electrode you see over here is the reference electrode, which is bathed in the reference solution of potassium chloride. And then you see it is sealed off. And this central portion is the pH electrode. It has got a glass bulb here, which is very sensitive to the hydrogen ion concentration. It has got an electrode in it, which are actually the platinum wires or the the metal wires, and they are connected to a volt meter. The two types of reference electrodes that come, you may have heard of the calomel electrode and the silver chloride electrode. So the silver electrode is actually a silver wire which is coated with silver chloride, and it is immersed in potassium chloride. Whereas the calomel electrode, if you have heard of it, is made up of mercurous chloride, and it is which uses mercurous chloride, and it uses mercury chloride in potassium chloride solution as a gel form or as a solid form. So two types of electrodes. So when you are ordering a pH meter, please look for the reference electrode, and it is always preferable to use a calomel electrode. Now, when this pH electrode is suspended in a solution, that means the solution that you want to measure the pH, because there are two electrodes and it is connected to a electrical voltage to a battery, you see electrical voltage is generated. The glass electrode, that is this glass electrode with the bulb, develops an electric potential that is directly related to this hydrogen ion activity, and that voltage is measured in the voltmeter and read in the pH meter as a change in the pH. So in a pH meter, you must have a reference electrode and you must have the pH electrode. The electrodes must always be suspended in potassium chloride. So the electrode should always be generally in saturated potassium chloride, which is 3 molar potassium chloride. And the bulb should not be exposed. You should not allow the potassium chloride to dry. Ensure that there is sufficient potassium chloride. Some electrodes come with a hole here and a rubber stopper, and very often the reference solution is lost or evaporated. Ensure that the electrode, the reference solution, is sufficient inside the reference electrode or the reference portion of the compounded electrode. Now comes to the most important part in analytical chemistry, and we will be doing all the calculations here. That is, how do you prepare a solution of defined concentration? And what is a solution? A solution is a homogeneous mixture which is created by dissolving one or more solutes in a solvent. So the chemical which is present in smaller amount is called the solute, and the chemical which is there in larger amount is called the solvent. So the method for measuring out the solute and solvent depends on the concentration unit that you are going to use. So for measuring the solvent or the liquid, we generally use either the pipettes or the volumetric flasks, or we use measuring cylinders, the graduated cylinders. And these type of solutions of defined concentration are required in almost all the analysis that we carry out in the laboratory, be it volumetric, colorimetric, preparing standards, whether it is HPLC, LCMS-MS, GCMS-MS, all or UV visible spectroscopy, we need to make a solution of a known or a defined concentration. So it is very important that we learn how to make these solutions and we know all the calculations. So the different solutions and the common units of what we use in the laboratory are molarity solutions, that is the molar solutions, which is a ratio of the moles of solute to the volume of the solution in liters, or normality, normal solutions. It is the ratio of the equivalence of the solute to the volume of the solution. Molality, which has the same, almost the same pronunciation as molarity, However, it is the moles of solute, the ratio of the moles of the solute to the kilogram of the solvent. So it is to the weight of the solvent, not to the volume of the solvent. It is represented by small m or lowercase m. We have the mass percentage, which is the grams of solute per 100 grams of solution, which is actually percent mass by mass. But very often in literature, you will find that it is written as weight by weight, but however, it is the same as mass by mass. Then you have volume percent, which is the milliliters of solute by 100 milliliters of the solution, and you have mass to volume, so you have grams of solute per 100 milliliters of the solution. And then I haven't put in PPT and PPB. You will see that in the later slide. So what is a mole? So a mole, if you recollect, way back in your +2 or even in the 10th standard, you would have defined a mole is the defined quantity of a pure substance that contains 6.023 into 10 to the power of 23 units. It could be atoms, ions, or molecules. And this is known as the Avogadro number. So in other words, a mole is the Avogadro's number. The SI units for the mole for the amount of substance is MOLE and the symbol is MOL. So therefore you see 1 mole of carbon weighs 12.0107 grams. However, it contains 6.023 into the 10 to the power of 23 atoms. Gold, on the other hand, 196.967 grams of gold also contains 6.023 into the 10 to the power of 23 atoms. So 1 mole of carbon contains the same number of atoms as 1 mole of gold. So that is the relationship between mole and atom. So the concept of mole allows the conversion of grams to moles and moles to grams. So let us look at this example. So a gold bar has a mass of 100 grams. So how many atoms of gold is there in this bar? How do you solve this? You have been given the gram atomic mass of gold. So what does this mean? It means there is 1 mole of gold. In 1 mole of gold, there is 196.67 grams. So we need to find out how many moles of gold there is in 100 grams. That is the first step. You first find out the number of moles that is present in 100 grams. So that is given by 100 divided by 196.67, and it is 0.5085. Now we know that 1 mole of any substance contains 6.023 into 10 to the power of 23 atoms. So now we have to find out how many atoms there are in almost 1/2 of the mole. So this could be approximately, if you do that, it is 3.06723 into 10 to the power of 23. Please see that we do not, when you have the powers, we do not divide or we do not subtract these powers. A second example, which is the opposite of this. Mercury is the only metal that exists as a liquid. A thermometer contains 0.0035 moles of mercury. So how many milliliters of that is it? It is just using the formula. When you see these questions like this, you should not think, oh, I don't, you have not taught us how to convert milliliters to that. You have to use all the formulas that you know, starting from density to Avogadro's number to mole to find out this. So what do we know? We know that the atomic weight or the atomic mass of mercury is 200.59. So this means that 1 mole of mercury is 200.59 grams. So we need to find out how many grams of mercury 0.0035 is. So the first step is to find out how many grams 0.0035 moles of mercury is. So we find out the mass of the mercury. We know, or you can get the density of mercury. And from the density, we know the density, it is 13.6 grams per milliliter. Here you have got 0.7 grams. So volume of mercury is given by mass by density. So mass by density is there. So in the thermometer, you have got 0.052 ml or 52 microliters of mercury in the thermometer. Now coming to molecular weight, or what is known as molar mass. This is the mass of one molecule is called its molecular weight or molar mass, and when expressed in grams, it is known as the gram molecular weight. When working with compounds, we generally use the term formula weight, which is nothing but the molecular weight, and it is provided on the labels of almost all the chemical bottles. So the molecular weight or the molar mass of a compound is simply calculated by adding the atomic masses of the elements present in the compound. So in these examples below, you need to calculate the molar mass of baking soda. So for this, what do you need to know? You need to have in mind the formula for baking soda. Baking soda is the common name, but what is the chemical name? It is sodium bicarbonate. So therefore, write down that baking soda is sodium bicarbonate. Then we know sodium is 23. I'm rounding off, we're not taking the decimals. Hydrogen is 1, carbon is 12, oxygen is 16. Since there are 3 atoms of oxygen, it becomes 48. And so you add 23 plus 1 plus 12 plus 48. So the molar mass of sodium bicarbonate is 134 grams. A similar question, calculate the molar mass of borax. These are compounds that you generally use in the laboratory, and you find in analytical procedures also, it says add borax. So you need to be aware of these formulas. So what is the formula for borax? Borax is nothing but the sodium tetraborate decahydrate. So here you have to take into account, because it is the decahydrate, we have 2 sodium molecules, 4 boron molecules, 7 oxygen molecules, and 10 molecules of water. So you have 23 into 2, 10.8 into 4, 16 into 7, and 10 into this. So the total molar mass of borax is 381.2. If we had said anhydrous borate, then you will not add the water. So please remember, when you're doing calculations with the chemicals for any weight purposes, for any solution purposes, such as molar concentration or normal concentration or molality concentration, please see whether it is in the hydrated form or it is in the anhydrous form, especially when you are making buffers. So what is the relationship between moles and mass? Moles is the mass divided by molecular weight. Very easy to remember. So to convert mass into moles, you divide by the molecular weight. To convert the molecular weight into moles, it is mass divided by number of moles. So To convert moles into mass, you need to multiply by the molecular weight. Okay, so to convert mass into moles, you divide by the molecular weight. To convert moles into mass, you multiply by the molecular weight. So here are two examples or two problems for you. One is you have to calculate the number of moles in 230 grams of anhydrous disodium hydrogen phosphate. So anhydrous very clearly says that means there is no water in it. So the solution, the formula for sodium disodium hydrogen phosphate is Na2HPO4. So the molecular mass of Na2HPO4 is given by 23 into 2 plus 1 plus 31 plus 16 into 4, or it is 126 grams. So the moles is equal to mass divided by the molecular mass. Okay, there is, I'm sorry, there is a mistake. There is the mass is given. Yes, it should have been 230. The mass should be divided by 126 and it should have been 2 moles. So you see, in the last step, I have made a mistake. It should be the mass, which is 230, divided by the molecular weight, which is 126, and it should be 2 moles, approximately 2 moles. So 230 by 126 is 1 point. Can we quickly do the calculation? So those of you who have your calculators or your thing, quickly do that calculation and make that change. It should be 230 divided by 126, which is equivalent to 1.825 molar. The second example is, what is the mass of 145 millimoles of sodium tetraborate decahydrate? So here the formula is given. So the molecular mass of 1 mole of sodium borate is 381.2. So you need to know, that means 1 mole is that. So 1 millimole will therefore be 381.2 milligrams. So 145 millimoles will be this multiplied by 381.25, or it will be 381.25 into, if you convert millimoles into moles, 0.145, you get 55 plus 55.274. Now we come to molarity and molar solution. So in the previous slides, you learned how to calculate the molarity of different solutions. So what is molarity and molar solution? A molar solution is defined as the number of moles. If 1 gram molecular weight is dissolved in 1 liter of the solution, it is known as a molar solution. So a 1 molar solution contains 1 mole of the chemical in 1 liter of the solution. 1 millimolar solution contains 1 millimole or 1,000 of the molar solution in 1 liter of this thing. Please remember here that it in 1 liter of the solution, and it is not in 1 liter of the solvent. So how do you prepare a molar solution? So preparing a simple solution of a specific molar concentration of a salt. So what this statement indicates is, it is not that you just weigh out the substance equivalent to 1 molar and you add 1 liter of the solvent. No, it is in 1 liter of the solution. That is what you need to remember. So now let us see how many grams of glucose is required to prepare 1 liter of 1 molar glucose. So this solution contains 1 mole of glucose per liter. And so how do you do? Step 1, you calculate the molar mass of glucose, which is 180 grams. Dissolve this in about 400 to 500 milliliters of water. Allow all the glucose to dissolve. Then take a volumetric flask and make up the volume to the calibration mark with water. So this solution contains 1 mole of glucose, or it is a 1 molar solution. Note, we do not add 1 liter of water to the weighed glucose. We dissolve the glucose and then we make it up to 1 liter. Now, examples of preparing a specific volume of a specific molar concentration. 1 molar solution, it is very easy to make because you need to just calculate the molecular weight, and what the molecular weight of the substance dissolved in 1 liter gives you 1 molar. Now let us look at a little more complicated solutions where you need to prepare 50 milliliters of a 0.15 molar solution. So the first step here would be to find out the molecular weight of sodium chloride. So you calculate the molecular mass of sodium chloride, and that is 58.5. The second step is we need to know the mass of the substance required to make the specific molarity solution. So what you need is, if we take the next step, the mass required, you can use this relationship. The mass that you require will be equal to the molarity. So here it is 0.15, the molar mass, which is 58.5, and the volume required, we have said 50 milliliters. So the volume is 50 milliliters, and divide by 1000. So substituting in the above equation, what you get is 0.15 into 58.5 into 50 divided by 1000. So therefore you need to dissolve 0.439 grams. You weigh this in an analytical balance, dissolve this in about 10 milliliters of water, and finally make up the volume to 50 ml in a standard flask or a volumetric flask. So when doing these type of calculations to millimolar, molar thing, it is very useful to remember that moles per liter is the same as millimoles per milliliter, and it is the same as micromoles per microliter. We are dividing both the numerator and the denominator by 1000, and so therefore moles per liter is the same as millimoles per milliliter, is the same as micromoles per milliliter. However, millimolar is 10 to the power of minus 3 molar, and micromolar is 10 to the power of minus 6 molar. So look at what the concentrations you have been asked to make, and accordingly make the solutions. So here is the other example where we need to calculate the mass of sodium chloride present in 100 ml of a solution which contains 1.5 millimoles per milliliter. So using the previous relationship, so here you have the molarity, it's in millimoles. Here is the molecular weight, the volume required is 100, and you have 1000. So this is 87.75 grams if it is 1.5. So you see you have 1.5 millimoles per milliliter, which is the same as millimoles per milliliter is the same as moles per liter. So therefore, it is the same as 87.75 grams. Okay. Another one, calculate the mass of sodium chloride present in 100 milliliters of a 1.5 millimolar solution. The reason I have given you this is to show you that 1.5 millimoles per milliliter is 1.5 molar, and this is different from 1.5 millimolar. So here you have the millimolar, 1.5 divided by 1000. So this is the molarity. This is the molar mass, 58.5. The volume is 100, and you divide by 1000. And so this solution will contain only 87.75 milligrams of sodium chloride. So a 1.5 millimoles per milliliter solution will contain 87.75 grams of sodium chloride, whereas to a 1.5 millimolar solution, you will contain only 87.75 milligrams. So making molar solutions is very important, because very often you are asked to make molar solutions from the concentrated aqueous acids or bases that are available in the laboratory, generally sulfuric acid, nitric acid, and hydrochloric acid. So how do you make the molar solutions? Because you do not want to weigh these acids, although you know the molecular weight. Because they are liquids, we don't want to weigh them. But if you look at, then how do you do this? So if you look at the label on the bottle of concentrated nitric acid, most often all the labels on the bottle will give you the molarity of the solution, the percentage purity of the solution, and the specific gravity of the solution. And so therefore, it is very easy for you to convert the volume of the solution into a mass, or the mass of a solution into volume. So concentrated nitric acid is generally supplied as 15.8 molar solution. So what that indicates is that 1 liter of the concentrated nitric acid contains 15.8 moles of nitric acid. So to make a 0.5 molar solution, you would have to dilute this 15.8 molar solution. So now if you take 1 milliliter of this solution contains 0.0158 moles. So now 1 mole of nitric acid will be equivalent to 63.29 milliliters. So to prepare a 0.5 molar solution of nitric acid, you will need to transfer 63.29 milliliters of nitric acid very carefully, okay, and take that 63.29 and add the acid, what you have, to about 500 milliliters of distilled deionized water. Then add more water to exactly the 1 liter mark in the volumetric flask. Whenever you're making an acid solution, please remember that you always add acid to water, and you never add water to the concentrated acid. The rule is acid into water and never water into acid. And you will see that when you add the acid into the water, there is heat produced. It is an exothermic reaction. So therefore, you must cool the flask and then only make it up to 1 to the calibration mark in the volumetric flask. So you can find these tables everywhere, which gives you the concentration of the acids, commercial acids and bases. What is their molarity, what is their purity. So you see, you have the molarity of these. Hydrochloric acid is 11.6 molar, hydrofluoric acid nitric acid is 15.8, and we have sulfuric acid. Okay, it's not in this table. You have sulfuric acid, which is 18 molar. Now, questions on these are, which of these dilute acids has the highest molarity? So, three dilute acids, which are all 50% weight by volume or mass by volume, and you have been asked to find which of these has the highest molarity. So, we need to calculate the molarity. So, we need to know the concentration of all the three concentrated acids as well as their molecular weight. So you calculate the molarity. So 50% is 50 grams per 100 ml, or it is 500 grams per liter. So 500 grams of sulfuric acid is 500 divided by 98, which is 5.1 molar. For hydrochloric acid, it is 500 divided by 36.5, which is 37.7 and 13.7. And 500 grams per liter of nitric acid is 7.9 molar. So this clearly shows that 50% nitric acid, 50% hydrochloric acid, the answer is 50% hydrochloric acid. So the next problem is make 250 milliliters of a 0.5 molar aqueous solution of hydrochloric acid. So how would you do that? So generally, the first step is to read the label on the bottle, which will tell you its molarity. Otherwise, you use the table, find the molarity. Although there are a variety of acids being supplied, the most common concentrated HCl is 11.6 molar. Some companies give you 11.8 molar. So remember to find out what is the concentration of the acid. Then use this formula for the dilution. That is, C1V1 is equal to C2V2. So here you can see there where V1 is the volume of the concentrated acid, molarity of the concentrated acid is 11.6, volume of the diluted acid required is 250 ml, and molarity of the diluted acid is 0.5. So the unknown is the volume of the concentrated acid that you require. So this formula tells you now that you need 10.8 milliliters of concentrated hydrochloric acid, and you have to dilute that to 250 milliliters. So again, do this using a standard volumetric flask. Now coming to the next one is normality and normal solutions. So what is the difference between normality and molarity? Normality is the number of equivalents of the solute per liter of the solution, whereas molarity is the number of moles per liter. And most of the normal solutions are used in titrimetric analysis. So normality is given by gram equivalents by volume, and you need to know the equivalent weight. So first calculate the equivalent weight, which is the molecular weight by the valency. So equivalent weight is defined as the mass of an element or compound which combines with or displaces 1 part of hydrogen, 12 parts, 8 parts of oxygen, or 35.5 parts of chlorine. And when expressed in grams, it is known as the gram equivalent. And generally, you can find out the gram equivalent if you know the valence of the solute. You divide by the valency. So the formula is equivalent weight is equal to molecular weight of the, for an acid, it is molecular weight of the acid by its basicity, and for an alkali, it is the molecular weight of the base by the acidity. So what is the basicity? The basicity is the number of protons it can give. So the basicity of hydrochloric acid is 1. The basicity of sulfuric acid is 2. So the equivalent weight of sulfuric acid is 49.4. The equivalent weight of nitric acid is the same as its molecular weight. So if you look at sodium hydroxide, it can accept 1 proton, so the acidity is 1. So in the case of sodium hydroxide, the molecular weight is the same as the equivalent weight. So common terms that you use with normality are normal solution, semi-normal, which is n by 2 or 0.5, decinormal, which is 1 by 10, centinormal, which is 1 by 100, and millinormal, which is 1 by 1000. And if you look at it, it is either 1 normal, 0.5 normal, 0.1 normal, 0.01 normal, 0.001 normal. So in addition, when you see this, you should be able to understand what is the normality of the solution. So how to prepare a simple solution of a specific normality? So the question here is, how many milliliters of phosphoric acid is required to prepare 1 liter of a 1 normal solution? So calculate the equivalent weight of phosphoric acid. Very clearly you see that the basicity is 3. So if you take the molecular weight of phosphoric acid and divide it by 3, you get 32.67. Okay, so take 100 to 200 ml of distilled water in a volumetric flask, add the weighed acid to the flask slowly, heat will be generated, cool it, add water to the 1 liter mark. This is one way of doing it. Here you are weighing the acid, that is, you're weighing 32.67 grams. The solution 2 is you can convert this 32.67 grams into volume and use the volume. The other solution is you have given, you know, the specific gravity of phosphoric acid, and you know the percent purity of the phosphoric acid, and from using the specific gravity and the purity, you can calculate the number of milliliters of phosphoric acid required to make this solution. So you will see that you require, using this, you require 23.01 milliliters. Solution 2, you just use the molarity of the acid, which is given on the label, and make, so the molarity of concentrated phosphoric acid is 14.3. So therefore the basicity is normality is molarity into basicity. So normality is given by 14.5 into 3. So it is 43.5 normal. So if you dilute 22.99 milliliters or 14 point normal to 1 liter, you get the same concentration. What I want you to see is whether we use solution 2 or solution 1, the volume that you use are almost the same. This is 22.99, and if we go back, we have got 23.01. Okay, these table numbers, please ignore them, because these table numbers are from the book which I have written about all these, how to do all these calculations. Now coming to how do you prepare a specific volume of a specific normality with salts. What we saw earlier was the normal solutions to be prepared from concentrated acids. Now we're looking at how to prepare normal solutions from salts. The first very simple one is how many grams of sodium hydroxide are required to prepare 50 ml of a 0.15 molar. So first step is to calculate the equivalent weight of sodium hydroxide. which is the same as its molecular weight, 40. So if you dissolve 40 grams of sodium hydroxide and make up to 1 liter, what you have is a 1 molar or a 1 normal solution. So to find out the mass in this case, you can use this relationship. The mass required is equal to the normality into the equivalent weight into the volume divided by 1000. Very familiar, isn't it? Exactly like that for molarity. There, instead of normality, we had molarity, and instead of equivalent weight, we had molecular weight. So substituting this, what you get is 0.3 grams. So you weigh accurately 0.3 grams of sodium hydroxide, dissolve it in about 10 ml, and finally make up the volume to 50 ml. This reaction is an exothermic reaction. So please cool the flask. And also sodium hydroxide is very hygroscopic, and also it can cause burn. So handle sodium hydroxide very carefully. Now, the next thing is how to make a normal solution from concentrated acids and bases. So we have gone through this. We have previous examples. So making 1 liter of 0.5 normal aqueous aqueous sulfuric acid. So look at the label. You will see that the molarity of sulfuric acid is given as 18. Then you know that the basicity is 2. So therefore, the equivalent weight of the acid, normality of the acid is 36 normal. So using C1V1, you can dilute the 36 normal sulfuric acid to 0.5 normal, or you can calculate the mass required, which is 27.78. But the in the lab, it is made by diluting a known concentration of using the formula C1V1 is equal to C2V2. Again, the precaution that you need to take over here is never add water to acid. Always add acid to water. It is an exothermic reaction. So cool the flask after making up the volume. Then you have a concentration which is very similar to molarity, which is molality and molal solutions. The difference between the definition for molality is the if 1 liter of 1 kilogram of solvent or 1000 grams of solution contains 1 molar mass of the substance, it is known as a 1 molar solution. So it is defined as the number of moles of solute per kilogram of the solvent. This is the difference between molarity and molality. So molality is per kilogram of solvent, whereas molarity is per liter of the solvent. So the SI unit is moles per kilogram, or small m. So molality is equal to moles of the solute divided by kilograms of the solvent. The spellings are similar, molarity and molality. So these cannot be interchanged because they are two entirely different things. When it is water, molality and molality remain the same because 1000 milliliters of water is equal to 1 kilogram, because the density of water is 1 gram per milliliter. However, when you use a different solvent, for example, we'll see the next example. However, when you use a different solvent as shown over here, ethanol, you will see that it is different. So now preparing a 1 molar solution of sodium hydroxide, of sodium chloride, calculate the molarity. It's 58.5 grams. You take 58.5 grams of sodium chloride. You measure out 1 kilogram of water. You add sodium chloride to it. You dissolve it in 1 kilogram. It will give you 1 molar solution of sodium hydroxide. So here you compare the molarity and molality of a solute which is dissolved in ethanol. For 1 molar solution, you dissolve 1 mole of the solute in ethanol, and the final volume solution is 1 liter. For a 1 molar solution, 1 mole of the solute is dissolved in 1 kilogram of ethanol, and 1 kilogram of ethanol, if you look at it, if you divide by the density, it is equal to 1267 milliliters of ethanol. So you can see the difference between a molar solution and a molar solution when the density of the solvent is different from the density of water. So then we have percentage solutions. So percentage solutions are 3 types, and the advantage of making percent solution is you need not know the molecular weight, you need not calculate the molecular weight, nor do you need to calculate the equivalent weight. It is simply means number of parts, units per 100 units or per 100 parts of the solvent. So the percent can be in terms of mass by mass. It could be mass by volume percent, or it could be volume by volume. All the 3 can be used to measure the concentration of a solution, and using the wrong type again here will result in incorrect final concentrations. So if you're using water, it is fine, but if you're using any other solvent, it becomes different. So please remember, when you have M by M, it's mass by mass, M by V is mass by volume, and V by V is volume by volume. So the letter in the numerator is always the solute, represents the solute, and the letter in the denominator represents the solvent, which is most often water. So these are the formula which are there for percent mass. As I said, very often, instead of mass by mass, we use weight by weight. It is equivalent to the mass of the solute by the mass of the solution into 100. Concentration is mass of the solute by volume of the solution into 100. And concentration percent volume by volume is a volume of solute divided by the volume of the solution into 100. And then you have the concentration, which is known as ppm, ppb, and ppt. So it is parts per million, parts per billion, and parts per trillion. These units are very convenient to use when the solute concentrations are very, very low, are very dilute, and instead of expressing in the terms of the number of zeros and then the last number, we can make mistakes in the number of zeros that we add. The regulators and scientists have chosen other ways to express these concentrations. So for example, if a solution has 1 ppm pesticide residue, it would mean that 1 gram of solution would have a millionth. So 1 part per million. Okay, so if you have 1 million parts, out of that 1 part is the pesticide. So this is equivalent to 1 milligram of pesticide in 1 kilogram of the solution. All the contaminants, if you see, when we talked about the contaminants, the pesticide residues, the heavy metals, the veterinary drug residues, they were all expressed in ppm. The metals were expressed in ppb. Additives are expressed in ppm. The limits are expressed in ppm. So how do we go about this? So ppm is the mass of the solute divided by the mass of the solution into 10 to the power of 6. And here the ppb is the mass of the solution by mass of solute by mass of solution into 10 to the power of 9. So it is the same as micro. Milli is 10 to the power of 3, 10 to the power of 6 is micro, and 10 to the power of 9 is nano. So now do this problem. If you have 155.3 grams of a sample of milk and it is found to contain 1.7 into 10 to the power of minus 4 grams of organophosphate, what is the concentration of the organophosphate in ppm and ppb? So you substitute in the equation. So it will be 1.74 into 10 to the power of 4 divided by 155.3 into 10 to the power of 6. So which is equivalent to 1.095 parts per million. The same thing, if you have to convert it into ppb, it will be, now we move this by 3 decimals in the front, so it is 0.01095 into 10 to the power of 5, so it is equal to 1095 ppb. So ppb is multiplied by 10 to the power of 3, so you have this. So to summarize all this and for you to remember, so concentration of the units, so you have percent by weight, gram of the solute by gram of solution into 100, gram of solute into milliliters of solution into 100, milliliters of solute by milliliters of solution into 100, parts per million is milligrams divided by kilogram, micrograms divided by gram, and nanogram divided by microgram. So what you need to remember here is when we are converting milligram to microgram, it is divided by 10 to the power of 3 kilogram. So you do the same thing for the denominator also. So if you convert micro into nano, again you convert the gram into microgram. So all these are the same. Similarly for ppm, milligrams per liter of the solution, micrograms per milliliter of the solution, and nanograms per milliliter, microliter of the solution. So parts per billion are now, if you look here, so now it is micrograms per kilogram, nanograms per gram, and picograms per microgram. So it's very important to know how to express in terms of ppm, ppb, in terms of when you are analyzing the contaminants. Now, how do you prepare stock standard solutions? In a laboratory, we generally make 3 types of solutions. One is the stock standard, the other is the working standard, and the last is the calibration standard. So the stock standard generally is a higher concentration solution of a stable analyte which we can store for a very long time. So the stock standard is made by any of the methods that I described previously. It could be in molar solution or normal solution or a ppm solution or a ppb solution. So make the stock solution and keep it. Then the next comes the dilution or the working standard. We generally dilute the stock standards into a working standard, and we have different ways of dilution. The simplest way of dilution is to use this formula. The concentration of the stock into the volume of the stock is equal to concentration of dilution into the volume of dilution. That is C1V1 is equal to C2V2. So if we want to prepare 100 milliliters of a 1.2 molar solution from a 2 molar stock solution, what do you do? So here is the formula. You have three knowns. You have only the fourth, which is an unknown. So you have C1, V1, C2, and V2. And you see the only unknown is the volume of the stock. So by algebraic rearrangement, you have 60 ml. So you take 60 ml of the stock and dilute it to 100 ml, and you get a 1.2 molar solution. Very often in the labs, we use the word dilution factor method, and you will see that we say diluted 100-fold or diluted 5-fold, and verbally we say 1 to 5 dilution, or we say 1 to 10 dilution. So how do you do this? This dilution factor is carried out by the dilution factor is equal to the final volume divided by the unit volume. So to make a 1:5 dilution, what you need to take is 1 unit of the stock and 4 units of the diluent and dilute it to get a 1:5 dilution, and your dilution factor is now 5. So taking this example, you prepare 500 milliliters of glucose solution that requires 1:20 dilution. So how do you do this? So if you see this is 20 dilution, divide the volume needed by the dilution factor. So you have 500 ml. So you divide by the dilution factor. So divide by 20, you get 25. So this is the unit volume. So now what you do is you take 25 milliliters of glucose, add 475 milliliters of water, and what you get is a 1:20 dilution. In the laboratory, many a time you will see solutions which are written as times. So you have 20x solutions or 10x solutions or 8x solutions. So what this means in the laboratory is you have to dilute it 20 times, or you have to dilute it 10 times to get a 1x solution. So in the molecular biology labs and in the microbiological labs, generally stock solutions are made, and they are made highly concentrated as 20x or 10x. So now when you have to make a dilution, the unit volume here is 20. So if you have to make 200 ml, so you take 200 divided by 20, so it is 10 ml. So you take 10 ml of the stock and you dilute it in 190 ml, and you get a 20 ml dilution. To do the dilutions more accurately, we do what is called a step dilution. And the step dilutions are done especially when you have the dilutions to be done such as 100 or 10,000 or 1,000 dilutions. So to be more accurate, we do a step dilution. So first you do a 1:10 dilution, and then you do a 1:100. So what you have got is 10 into 100, and that is 1,000. So the first dilution is take 0.91 ml and add 0.9 ml, you get 10. Now take 0.1 ml of this and dilute to 9.9. So you can do step dilutions, and your final dilution will be dilution factor 1 multiplied by 2 multiplied by 3. So it could be 10 or it could be 100. And in the microbiology, you see, and in terms of ELISA and PCR and other sophisticated techniques, to get accurate results, we do what is called as a serial dilution. So the serial dilution is the same as the step dilution, but we keep the dilution factor from the first tube to the second tube common, not 10 and 100. So every tube would be a 10 dilution. So you would have 10 into 10 into 10 and so on. So if you want to make a 4-step dilution, so for 1:100 dilution, and you want to start, this is very important, especially when you do bacterial culture dilutions. So here the initial step takes 1 unit volume of the neat bacterial culture, which is 20 microliters, with 1980 microliters of broth. So now what you get is, you get 20 in 2000, which is a 1:100 dilution. In the second step, if you take 20 microliters of the first dilution and you again transfer into 198, what you get is 10 to the power of 2 into 10 to the power of 2, which is 10 to the power of 4. If you repeat the dilution the same way, where you take 20 microliters from this and add to 190 microliters, 1980 microliters of the next tube, you get a 2 into 10 to the power of 2 into 10 to the power of 2, which is 10 to the power of 6. So you can do accurate dilutions to get almost 1 CFU if you know the colony forming units of the first one. So in bacterial cultures and in these laboratories, and also for ELISA, we use what is known as the serial dilution. But you must remember to vortex the tube thoroughly so that your results are accurate. So this is how the serial dilution is done. So you have 2000 of the first, take 20, add it here, mix it well, take 20, add it to the next tube, mix it thoroughly, take 20, add it to the next tube, mix it thoroughly, and then, so you see the color is also changing and the dilution factor also is increasing. So these are formulas which you can use for conversion between units, how to convert moles to grams to mole, number of moles in V milliliters, moles per liter to grams per liter, grams per liter to moles per liter. You should know all these, and percent solution to molarity, molarity solution to percent solutions, normality to molarity, and molarity to normality. You need to know interconversions between all the units that I have discussed in these slides. So then we come to the last part of it, where we have the acids. So you need to know what is the difference between a strong acid and a weak acid. So the strong acids, if you look at the strong acids, these acids dissociate completely when put into water. So look at this: hydrochloric acid, nitric acid, sulfuric acid, they are completely dissociated into the protons and into the analytes, that is the accepting analyte. And what I want you to look at is to see that this is a single direction arrow showing that there is complete ionization of the acid. So the arrow points only in the right. So strong acids dissociate completely into their ions in water, yielding 1 or more protons per molecule. On the other hand, a weak acid does not completely dissociate into ions in water. For example, if you have an acid, weak acid HA, in the solution, you will have a proton, you will have A minus, and you will have some unionized HA. So the best example of a weak acid is acetic acid. So when you add acetic acid to water, you see acetic acid will dissociate into the H plus, which can bind with water to form the hydronium ion, and you get the acetate ion. But here you see the arrows are both ways. So these arrows are pointing both ways, indicates that only a small amount of the acid is dissociated into the acetate ion and into the proton. So if you compare, please remember that the strong and weak acids are different from concentrated and dilute acids. A concentrated acid is one which contains a low amount of water. In other words, the acid is concentrated. A dilute acid is an acidic solution that contains a lot of thing. So if you have 12 molar acetic acid, it's concentrated, but acetic acid is still a weak acid. It is not a strong acid. On the other hand, if you have a very dilute hydrochloric acid, that is 0.0005 molar, it is still a strong acid, but it is a very dilute acid. So this is to tell you what is the difference between strong acids and weak acids, and it is not the same as concentrated and diluted acids. Mineral acids are acids. These are terms that you will hear, so that is why I'm putting it to. Mineral acids are acids which are made from inorganic ions, and all of them will form hydrogen ions and the conjugate base when dissolved in water. Some of the mineral acids are known as the bench acids, and those bench acids are hydrochloric acid, sulfuric acid, and nitric acid. That is because these are most commonly used in the lab. So the list of mineral acids is given here: hydrochloric acid, nitric acid, phosphoric acid, sulfuric acid, boric acid, hydrofluoric, hydrobromide, perchloric, and hydroiodic acid. So how do you prepare buffers? Buffers are solutions that resist change in pH on dilution or on addition of small amounts of acid and alkali. We use them very often in the laboratory for analysis, and they consist of two components. One is the weak acid and the other is the salt of the weak acid. So generally it is a weak acid and the salt of the weak acid which is used to prepare a buffer. So the buffer is prepared in solution. So in solution, if I take acetic acid, I take acetic acid and I take the acetate. Now acetic acid can dissociate into acetate and the proton thing. This system can take a proton and still there may be no change in the pH. They can give a proton and still there will be no change in the pH. So that is what a buffer is. The system can absorb either a proton or a hydroxyl group due to the reversible nature of the reaction. And when it releases a proton, it will neutralize the OH to form water. And the conjugate base can accept the proton to form the acid. In this way, these three species will be constantly adjusting and being in equilibrium because you have this forward and reverse reaction. So a solution of sodium acetate and acetic acid makes a very good buffer. So how do you prepare? There are two types of buffers. One is the acidic buffers and the other is the alkaline buffers. So the acidic buffers work in the acidic pH range and the alkaline buffers work in the alkaline range, and we have some neutral buffers which work in the neutral pH. So depending on the pH that you want to work at, you can choose which buffer you want. So if you want to work in the range of 4.5, you can use either acetate buffer or you can use a citrate buffer. If you want to work in the pH range of 8, you can use a tris-HCl buffer. So how do you calculate the pH of aqueous buffers? We use the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation is that the pH is equal to pKa plus log to the base 10 of the A minus divided by HA for a weak acid which dissociates in the way that it is shown. So Ka is the dissociation constant of the weak acid. A minus is the concentration of the conjugate base, and HA is the concentration of the weak acid. So using the Henderson-Hasselbalch equation, we can calculate the pH of buffers. So here are examples that we need to work out. So here is calculate the pH of a buffer solution containing 0.1 molar acetic acid and 0.1 molar, it should be sodium acetate. The Ka of acetic acid is 1.74 into 10 to the power of minus 5. So if we calculate this, what you get is that the pKa, first you convert the Ka into pKa, you get 4.76, and then substituting in the Henderson-Hasselbalch equation, you get the pH of the acetate buffer is 4.76. Now in this example, you say calculate the pH of a buffer solution containing 0.5 molar acetic acid, and this should be 0.25 molar sodium acetate. Okay, it's not acetic acid. Sorry for the mistake. The Ka of the Ka for acetic acid is 1.7 into 10 to the power of minus 4. So now we know, we have calculated in this problem the pKa, which is 4.76. So using the Henderson-Hasselbalch equation, we say pH is equal to 4.76 plus log of, we have the thing 0.25, that is the acetate, 0.5 is the unionized acid. So what you get is the pH of this acetate buffer is 4.46. So what is important to see is that although the concentration of the acetic acid has changed from 0.1 molar to 0.5 molar, and the sodium acetate has changed from this to the, you see the pH has changed only from 4.76 to 4.36. So this change is a very small change. There are different types of glass that we use in the laboratory. So you need to know which glass you are using. So we have the consumer grade glass or soda lime glass, which is generally used for all the reagent bottles that you use. And soda lime glass, the temperature you can use it up to is 150 degrees Celsius. The soda lime glass is also employed as a material for pipettes. Then you have the borosilicate glass. This is the glass that generally you must use in the laboratory, and this glass can withstand thermal stress, and it can withstand work temperature up to 280 degrees Celsius. But however, you cannot use hydrofluoric acid with borosilicate glass. So understand which glass the material is made of. Then you have fused silica or quartz glass. This glass you use when you have to heat up to 450 degrees Celsius. So therefore you look at this when you want to do, especially in the case of crucibles when you're doing ashing, and you use quartz cuvettes because it is transparent to UV light. You get darkened brown glass or amber colored glass, which is used generally to store reagents or things which need protection from light. Heavy walled glass is strengthened to withstand high pressure reaction. So any high pressure you use. Fritted glass is a glass which has got pores, and you use this for filtration, and it is also known as sintered glass. Coated glass is specially treated glass. And then you also use siliconized or silanized glassware to prevent organic samples from sticking to the glass. Okay. Please read this up, and you need to understand what is the classification of the laboratory solvents that are used. So we have different grades of solvent. And when I take HPLC, probably I will repeat this because it has the time I have taken quite a long time, but I wanted to get through all these problems so that all of you understand how to do these problems, interconversions, because a large number of questions you get, are problem oriented, where you have to do these calculations. So I will just go through the classification of solvents when I take the class on high performance liquid chromatography. So the next webinar will be tomorrow on biological techniques, that is the DNA and protein based assays. The second part of this lecture, as I said, on volumetric and gravimetric analysis will be taken on May 16th at 11:30.